Today, we are getting even funkier with it. And it's not that crazy of a circuit, actually. I think this was, if I remember right, the last one and this one are actually guitar pedals. But it's really not too crazy. It's not too bad at all. This is a reasonable circuit to look at. This isn't anything super crazy. You know, building something like this is not actually that bad. But anyways, let's talk about how we got here in the first place, right? And why we're staring down things like this. We started chapter 27 talking about current and flow of charge and all of those things, and then we talked about resistance, and then chapter 28 said, okay, that stuff is cool, but let's talk about how it actually affects all of the devices that we use, right? The devices that we use right now, that we turn on the light, all of these other things, let's talk about how those things actually work, how we can discuss them. So we started with that. We learned about Kirchhoff's loop laws that tell us how to solve any circuit, and we're just going to essentially keep moving from there, right? We started from a very simple circuit, one battery, one resistor, then maybe two resistors. And then last time we started talking about more combinations that we could possibly have of those things. For example, if we have a bunch of resistors in series, it looks just like this. That means we have a bunch of resistors all along the same wire. And being along the same wire, that means that the current going through each one of these is exactly the same, conservation of current. But the way that we would write an equivalent resistance, right? Because all of these things are acting as obstacles in the way. There's an equivalent resistance that we could plug in one resistor instead of these three, and it would act exactly the same. And to find that resistance, all we have to do is sum up all of the resistances. If it's 3, 4, 5, 60 resistors, however many, if they're all in a line, sum up all of their resistances, and that's what we get. And there's a couple different checks we can use to make sure that we're on the right track with these things, right? More obstacles in the path means that it's going to be harder to get through that path. My final resistance, my equivalent resistance, should be greater than any individual component going into it. If it's not, something's wrong, because it's more obstacles in the way. Now, we could also open up more paths. We could have multiple paths that we could go through, and this is called parallel. So a bunch of parallel resistors means that, for one, the potential difference over each of them is exactly the same, but the current will now split up. I've got 3 different paths for the current to go through. But we find the equivalent resistance using a reciprocal sum this time around, which means that any time I make parallel resistors, the resistance of the ensemble goes down. It's more paths, even if they're bad paths. Even if they're difficult paths to get through, more paths means more opportunities for the charge to flow through, means a lower resistance in total. So keep that in mind. If you see parallel resistors, resistance goes down. If you see series resistors, resistance goes up. So let's keep going on with these loop rules, and let's figure out how can we solve any of these, any sort of system we might see. So I've got a step-by-step process here. Let's imagine that we have something like this in front of us. Now we're in a little bit of a sticky situation. There are 2 batteries here. There are 2 batteries, and not only that, but there's 3 different channels, kind of. There's all sorts of stuff going on here. So what do? We don't have any sort of rules about combining batteries. And there's a good reason for that, because it doesn't work like resistors. Every single time you see a battery along a path, you can't collapse that path. That battery messes everything up. This is only true if it's only resistors. If it's only resistors. So here, there's nothing I can do. I can't simplify this circuit. I can, technically. I could combine R4 and R1 because they're along the same line. Even if there is a battery in the way, because they're along the same line, I could technically combine them, but that's the only thing I could do. And it's not going to save me that much work, so I'm just going to leave this thing as is. So step 1 is figure out if we can collapse anything, and then if we really care enough, right? It's an optional step. Second step, these orange lines that I've got right here. Guess what direction the currents are going. Look at every individual current that we might find, right? So I've got 3 different lines. If I'm looking at this junction, 1 current comes in, 2 currents come out. If I look at this junction down here, it's the same, right? I1 comes in, I2 and I3 come out, then I2 and I3 come in, and I1 goes out. It's the same kind of deal. I could even be a little bit more rigorous with this thing if I wanted to, and I could label down here is also I1, just to make sure that I'm keeping track of everything properly. So, but remember, it's guesses, right? It doesn't actually matter what we're doing here. I can base this guess off of anything. Next, we're going to draw out the equation that describes those all those currents that we just guessed. So in a case like this, point A, point B, it's the same equation, right? I1 on one side, I2 and I3 on the other side, right? So it's unique. Point B would not give us a new equation, so we don't need to write it again. Okay, then I'm going to go through the loop rule. Now, here's a little bit of a tricky thing, and somebody called me out on this one earlier. There's another loop that I could draw. But it wouldn't be another unique loop, is really the trick here. And this one's a little bit hard. This is probably the hardest one to figure out before you've done a lot of these things. It's a little bit difficult to determine when it's going to be unique and when it's not going to be unique. So here's what it comes down to. When I take the left loop and the right loop, I've already considered every single component that I've got. If I were to draw a third loop around the outside like this would be another valid loop, but it would be a redundant equation because it's already considering all of the components that I've already looked at in my other 2 equations. If I tried to combine those 3 equations now, if I didn't consider my junction equation, but if I looked at my 3 loops, I might come out with an answer at the end like I1 is equal to I1. When you're solving out some of these problems, you'll get answers like this. 0 is equal to 0, 1 is equal to 1, stuff like that, right? It's meaningless. Of course, I1 is equal to I1. Of course, 0 is equal to 0. All of these things, they don't give us any information. If you end up at this, that just means that you had a redundant equation somewhere. It's not a big deal. Just take another look. Make sure that you're not just kind of doubling up on what you're counting. Right? But if I don't have that one, if I just have my loops that I've already drawn out here, not this really big one, but just these 2, I count out my equations. I say I've got 1 equation, 2 equation, 3 equation. I had 1, 2, 3 unknowns. This is now a solvable system of equations. And how do we solve systems of equations? We think very hard and then we write down the answer. That's all there is to it. Now that you have hopefully stopped laughing and not just screaming, this is my insertion for some sort of Richard Feynman joke. The context for this is that I think it was when he was receiving his Nobel Prize, somebody asked him how he solved problems. And he explained it's very simple. He just writes down the problem, thinks really hard, and then writes down the answer. So it's the Feynman method of doing physics. For the right loop, wouldn't it pass through battery 1 in order to return to battery 2? Not for this path right here. If we take this path right here, it forms a complete loop without going through the batteries. If we look at the outside loop, then we would indeed go through both batteries. But that's okay. That's okay to do that. That's all fine. We would just count it in our loop equation. It doesn't have to be only, and we're going to see some of these problems that'll have stuff like that. Yeah, you don't always have to go with the current. You can pick any direction, because that kind of goes with our idea of make a guess. Make guesses. They don't have to be good. Right? If they are good, then you get more positive answers at the end, but you get more negative answers if you make bad guesses. Who cares? The magnitude would always come out to be the same no matter what. The negative just means you guessed the wrong way. Now, for actually solving out these systems of equations, there are a couple different ways that you can do this one. I'm going to go through the algebra method because I don't like matrices very much. But I do recognize that the matrice method is significantly easier and much, much faster because there are calculators for it. And that is not a small detail. So when you're doing a lot of these problems, I do recommend go ahead and look up how to solve systems of equations with matrices, right? Or have a matrice calculator. I'm not going to be offended or counted against you or anything else. It's a prerequisite that you know how to do algebra and go through systems of equations. But I'm not going to be constantly testing to make sure you can transform all of these equations, right? I assume that you know how to do it at this point. So use a calculator for it, right? Make your own life easy. I'm going to keep doing algebra for today, but in your own practice, I do recommend the matrice method. Speaking of, here's your first chance to try it out. So an ammeter is a device that measures current. So it reads I, but it has no resistance by itself. It's a device that slots right in the middle of the wire and it just reads the current passing through. It tries to not have any resistance to not upset anything in the current. So it's just telling us that the current going through this middle wire is 3 amps. Now, we don't know I1, we don't know I2, and we're looking for E. So we need 3 total equations. 1 junction, 2 loops. I want you to take this picture, guess what direction I3 is going, draw it on the picture, and then start writing out those equations and try and solve this one out. Okay, so I'm going to say, let's go ahead and start to take a look at this one. So the first thing I need to do is make a guess. Let me go ahead and steal this color. So, making a guess here, there's nothing I can do to collapse this. First of all, there's nothing I can do to simplify this circuit. It's already as simple as it's possibly ever going to get. So I'm going to immediately jump to step 2 and make a guess for my third current. I1 and I2 are already determined for us, but let's go ahead and look at this junction right here. I1 comes in, I2 comes in, I3 goes out. That seems reasonable to me. So let's do that. Call this I3. Then our equation for this junction is just going to be I1 plus I2 is equal to I3. Okay, so that's one equation, but we've still got 3 unknowns, so we need to start drawing some loops here. Let's go ahead and do one of these in orange. So I'll just take a left loop and a right loop. Do this one right here, and then let's also do dark green. Why not? Do a loop like this. Making these kind of nonsensical, whatever they want to be. It doesn't matter too much. So if I were to draw my orange loop, I'm going to pick a starting point, and let's say my starting point is right here in the bottom left corner. Then in order, I go through my battery from negative to positive. So that will give me a positive 9 volt potential difference. Then I go with I1 through that 3 ohm resistor. So that's a minus I1 times that 3 ohm resistor. Then I go down and I go with I3 through the 2 ohm resistor. So that's another minus. And then I go through the ammeter and I'm back to my starting point. Okay, now I'm going to look at the right loop. Let's go ahead and pick this as our starting point. So our first thing that we do is we go against the current through the 2 ohm resistor. So that is going to be a positive I3 times 2. Then I go against my current through the 4.5. So that's another positive. Finally, I go against my battery to get back down to my starting point, so that's now a minus curly E. Okay. And these are our three equations, right? We've got 1, 2, 3 for three unknowns. That's enough to start solving it. So what I'm going to do now is we've got to figure out some way. I see my two big equations on the bottom, I1, I3, I3, I2. So let's go ahead and rearrange this top equation here. We already know what I3 is, right? I3 is 3 amps. So if we already know what that's supposed to be, and let's roll with it. Let's see what happens. We already know that one's supposed to be 3 amps. We already know what all of these other values are. So I'm going to go ahead and just write that out real quick. Just so we can keep track of that thing. So now, knowing all of that, I can solve out actually either one of these kind of right off the bat, right? I can't solve out E though, because, well, I take that back, because I should, let me retract the statement just a little bit. I can't solve out either one of these right off the bat. If I look at my bottom equation in dark green, I know I3, but I don't know I2 and I don't know E. That's two unknowns, I can't solve it. My top equation in purple, I don't know I1, I don't know I2. I can't solve it. But my orange equation, I can solve this right off the bat. Plug in my 3 amps. So this is 9 minus, and I'm just going to move some things around a little bit. So 3I1 minus 2 times 3. I1 is equal to 1 amp. So we've got our first answer. Now that we know what I1 is, I still can't solve my green equation because I still don't know I2. So I'll go back up to my purple equation and I can plug in my 1 amp now. So that would become, I'll write this in purple, so we're color coding this thing. Now this is 1 plus I2 is equal to 3. Hopefully we're all on the same page for this one. I2 is equal to 2 amps. And that means that if I go to my green equation now, I have all of the details that I could possibly need for this thing. I'm going to start plugging in some of these numbers. Let me move the E to the other side. So we'll say I3 times 2. I3 was 3 amps. 3 times 2 plus 2 times 4.5 is equal to curly E. 6 plus 9, E is equal to 15 volts. And there we are. When we solve the circuit on the way, just for fun. So let's go ahead and keep moving right along. We've got another one. We've got, honestly, a kind of similar looking circuit, but this time around, we know what the batteries are. We're looking for all 3 currents this time. And one thing that I do want to kind of point out here is this is not such a different thing than what we just saw. I know it looks a little bit lopsided and a little bit weird, but realistically, this circuit could just as easily be drawn just like this. There's really not any sort of difference. If it's a little bit lopsided, so what? Because, I mean, look at these things. This junction matches to right here. This junction matches to right here. It's a little lopsided, but so what? That's the only real difference here. So keep that in mind. Don't be spooked by the fact that it looks a little bit strange. Don't get confused. Don't think anything is parallel that it shouldn't be. I can't reduce this anymore. This is already as reduced as possible. All right, let's go ahead and start taking a look at this thing. So, as I've got it, I need to make some guesses to start, right? Which I have forewarned you about now. There are guesses to be made in some of these problems. So what we're going to do, I'm going to make my guesses in, we'll do these in late green this time around. I like to do green for current. And then, let's make some random guesses. Let's see what we get. Let me go up on this one. Call this I1. Then I'll go for the middle one, and let's say it comes back down through this one. I2. And then I see the battery here, so I'm going to say that this one probably goes like this with the battery for I3. Then I would look at one of my junctions, this one right here, for example, and I would say, okay, I1 splits into I2 and I3. I1 comes in, I2 and I3 come out. So there's my junction equation. Down here is the exact same junction, right? More or less, it just recombines. So then I'm going to need to start drawing some loops. Let's do one loop right here. And let me go ahead and write that out. So I'll start from this corner right here. So the first thing that I see, I go along with the battery, so that's 12. Minus, because I go with the current, 4 times I1. Go with I2 through the 2 ohm resistor, so that's another minus 2 I2. Then I get back to my starting point. Now I'll do another loop in blue, and let's go ahead and go like this. And I'll start from this corner right here. And that means that the first thing that I see is my 15-volt battery. And because I'm going along with the battery the entire time, that's a positive 15. Then I go with current I3 through the 4 ohm resistor, so that's minus 4 I3. And finally, I go against I2, so that's plus 2 I2. Okay, well, we've got all of this stuff. Now, what can we do? I've got 3 equations for my 3 unknowns. I'm ready to start solving this thing, but there's not a clear-cut way like last time. I can't just immediately start plugging in a few different things to whatever and seeing what happens. Right? I don't have one equation that's already ready to be solved like I did in the last one. So for this one, we're going to have to do a little bit more substitution. Now, I'm going to bring this up again, that if you are doing the matrixy method, it is so much faster if you can just plug this into a calculator and be done with it. So I do recommend that. But for me, here, I am not a huge fan of the matrices, so I'm going to start doing some substitutions and seeing what I can get. Combining equations 2 and 3 would not actually get us that much progress, because that would get us I1 and I3 together, but there's not a lot we can do with that, unfortunately. So what I'm going to start with here is let's plug I1 in. Let's take equation 2, let's plug in I1. It's the easiest way to approach this, I think, or the simplest start at least. So this is minus 4 times this from green. Now I'm also going to have my 2I2. Okay, and now I might consider, well, no, I'm not going to consider stacking these 2 equations. Now I've got things based on 2 and 3. So let's just simplify this first. Let's distribute what we've got in green here. So this is going to become 12 minus 4 and then a minus 2, so minus 6I2. Minus 4I3. Okay, and now I'm going to pull off a little clever trick where I can subtract one equation from the other. So let me subtract my blue equation. And I'm going to rearrange it real quick. So let me move the plus 2I2 right here. So I can move the minus 4I3 right here. Whoops. I want to make sure, because realistically what we're doing here is we're subtracting 0 from 0. Still 0, right? No change there. That's what these equations are trying to say. This whole equation is equal to 0. So if I subtract 0 from 0, who cares? Right? It's the addition identity. So in doing that subtraction, what do we get at the very end of this thing? 12 minus 15. Negative 6 minus 2. Negative 4 minus negative 4. So there we are. I3 is equal to a positive, no, just kidding, negative 3/8. Did I do something weird here? What did I do? Isn't that I2? Yes, it is. Ha ha! I was going to say, something is very wrong. Something is very wrong. Yes, because I3 just canceled. It's I2 that got left over. I kept looking back at the original ordering of this. So, what did I do here? I guessed wrong. I got negative 0.375 amps. Oh well. So I goofed up the direction. Who cares? I still got the right magnitude, and now I know what the direction actually is. But I can't change anything yet. Do not change anything yet. You guessed wrong. That's okay. We're going to move along with that because that wrong guess was the basis for our 3 starting equations. We can't change it now and expect all of these answers to keep working. So we're going to solve this thing out, and then at the very end, we can tell ourselves what the actual directions should be. So now that I've got I2, I'm going to go back up to my equation in blue here. I'm going to say this becomes 15 minus 4I3 plus 2 times negative 0.375. Plug it in exactly as it comes in. So now, because I keep messing up a lot of these numbers, this is going to become 15 minus 4I3, minus 0.75. $14.25 divided by 4 is equal to I3. Plug it in real quick before I mess up my arithmetic, because I've had a habit of that today. I3 is 3.5625. There's our second current. Now, we go back to our very last one. We say, okay, I1 is equal to I2 plus I3. Combine those two answers together. I1 is equal to 3.1875. And this is why we have to keep it until the very, very end. Because now we can flip directions around, because we've already done the solving. We know what the magnitudes of the currents are, and even realistically, by knowing whether it's positive or negative, we've solved out for the direction as well. Right? But this is fine. You just have to pick a direction and roll with it until you're finished with the problem. Finish the problem before you try to change directions on your picture. Right? Or even just draw a new picture. That's probably the better approach. Leave this, draw a new picture with the proper currents, the proper directions that it should have. But let's take a look at this and let's see what's actually happening here real quick, because what led me to a wrong guess? Well, this was an interesting thing. I assumed that 12 volts would push the current up, and then the current would wrap back down and into the bottom of the battery. So why didn't that happen? Well, it's because there's 15 volts on the other side. They both had the same resistance. It's 4 ohms and 4 ohms. So what was going on then? In my red loop, the 12-volt battery is trying to push some current going this way, right? That's the general idea. The battery's pushing some current, pushing this way. The 15-volt is trying to push a bunch of current going this way. But the 15 volt faces less resistance. And it's a stronger, it's a larger potential difference, and it faces the exact same amount of resistance that the 12 volt did, so it's got a stronger push by the time we get to our 2 ohm resistor. If these were both 15 volts, we would find that there's no I2. They would completely cancel each other out. And there's all sorts of fun devices that do this. There's, a bunch of different sorts of bridges that you can make in circuits that will balance themselves out or have things like that, help you set different values to try and balance different circuits. It's a very neat little feature here, right? And we can kind of see that represented in the numbers as well, because I1 and I3 are both greater than 3 amps, and then I2 is barely above 0, right? They're certainly pushing against each other. But also, yes, these problems will take up a lot of space. Don't be afraid of that. Use that space. I've talked about this before. Like, I take a ton of space when I do these problems, and it's the best way to do these problems. Don't be afraid to take up a lot of space. Let's look at another one. And I'll show this again, because we'll make some guesses that may or may not be correct. Because we've got another one here, where now we have 3 batteries, a battery along each path. So again, there is nothing we can do to collapse this circuit. It is already as simple as it's going to get. Don't try to collapse this one. But we're looking, you're going to need to solve out for all 3 currents. The Canvas answer is specifically for the bottom 5 ohm resistor, but solve out for all 3 currents. But we're still looking for 3 equations at the end of the day. So guess some currents. They don't have to be correct. They can be correct or incorrect. It doesn't matter. Stick with them until you finish the problem. And then you can draw another picture with corrected directions if you'd like. All right. Good time to start looking at things. Well, I should probably copy the picture first, shouldn't I? Let's make sure we grab that and take it with us. Okay, so we need to make some guesses, right? That is the first step of all of these problems. And so what I'm going to do, there's a bunch of different ways you can do this. Like when I keep saying good guesses, you kind of go with it. You see what you do. One common thing that we might see is that most of the time, maybe not 90%, but most of the time, current comes from the positive end of the battery, goes into the negative end of the battery. So I might guess that this is my direction. I said this is my direction for I1. I'm going to call that I1. This is my direction for I2. This is my direction for I3. I might be right, I might not. It doesn't matter. Now, let's go ahead and look at one of these junctions real quick. So this junction right here, for example, I2 comes in, I3 comes in, I1 comes out. So there is our equation in green. Time to make a loop. I will start my first loop, looks like this. And I'll start in the top right corner, or top left corner. Top left corner. Whatever directions are. So as I go through my loop, the first thing that I see is this 10 ohm resistor. I am going with the current. So that's a negative 10 I2. And then we go with the battery, so that's a positive 3 volts. Then we go with the current, I1, so that's a negative 5 I1. And finally, we go with the battery, 12 volts, so that's plus 12 volts. There we are, all those pieces. Now, I'll do a blue loop, and let's go ahead and go like this. Just make it in the same direction. Doesn't matter too much. I'll start from this corner right here. So I go down, I go through the 5 ohm resistor first. I'm going with the current, so that'll start as a negative 5I3. We go with the battery, so that's plus 9. Then we come up and we go against the 3 volt battery, so that's minus 3. And then we go against I2, So that's plus 10I2. Three unknowns, three equations. We're ready to start solving things. So I'm going to take the same process as last time. There's nothing super clever that I think I can do here. Yeah, there's nothing super clever. So I'm just going to plug in the green equation to the red equation again. Let's just do that. So that means negative 10I2. Make that I a little bit more complete. Let me combine the 3 and the 12. Let's just do that real quick. And then we have minus 5 times, here's where we're subbing in our green equation. Is equal to 0. Okay. Let me simplify it one more time just so we have these terms kind of spread out. So negative 10 minus another 5. And I'm going to pull the 15 out front. Okay. What do I see? Well, I've got a negative 5I3, so I think I'm going to do the same subtraction thing as last time too. It's a pretty consistent method for me. Let's rearrange some things real quick. So 9 minus 3 is 6. Let's combine let's move the I2 over to be right here. And the I3 is in the final position. With all of these things together, oh, there we are. With all these things together, 15 minus 6, 15, or negative 15 minus 10, negative 5 minus negative 5. .36 amps. There's our first answer. Same process as last time. Go ahead and plug this thing into our blue equation again. Plus 6. All of this stuff, so this turns into 3.6. I3 is equal to 9.6 divided by 5. Should come out with a final answer for this one. Type that same thing in wrong last time around too. 1.92 amps, which I believe is our I3 is the one that we're actually interested in, right? And in the Canvas questions. But let's go ahead and finish it out because we're right here. We've got I2, we've got I3. Combine them together to find I1, and we should find that I1 is equal to 2.28 amps. And there we are. How did you know 3 was negative for the blue equation? You mean my first term right here? Or the battery? For the battery, because I'm going against the battery. So I have low potential on this side, high potential on this side, and this is, I know I'm looking at the 9 volt. So going in the loop in this direction, I'd be picking up a positive 9, but if I'm starting on the high end and I'm going to the low end, and I know the magnitude is 3 volts, then I'm losing 3 by going right to left. Well then, I do have one other topic that I do want to talk about here. And this is really just, this is not anything crazy. This is like not a new conceptual thing or anything else, but this might be useful if you're trying to troubleshoot any sort of circuits, right? Let's say you're working on circuits and you're trying to troubleshoot something, which if you are working with circuits, you are absolutely going to have to troubleshoot it because that is 90% of the work with circuits. But let's say you want to troubleshoot it. How might you troubleshoot it? Well, I have a multimeter, right? And that multimeter can tell me the potential difference between two different points on the circuit. Let's say we put the black probe at this point P over here, and we wanted to check what's the potential difference right here. I can read it off of the multimeter, but is it what it should be? How can we tell? Well, what if we don't go all the way around in a loop? Remember the entire idea behind the loop was that if we come back to our initial position, we should have a zero potential difference from when we started, right? Final minus initial should always be zero. But if we don't go all the way around, that rule doesn't apply anymore. Every component provides some sort of potential difference. Then going through all those potential differences, and then ending some point prematurely before we get back to our initial starting point, we'll have a potential difference. And that's fine. But that can be a way to check to see if your circuit is doing what you think it should be. Because if you calculate out what this should be, and your multimeter does not read that value, something's wrong. And you could use as many troubleshooting methods as possible with circuits because everything can go wrong, and it's a disaster. But that's the idea, right? You can always just calculate a potential difference. This is really just an extension of what we have already been looking at. You just don't go all the way around the loop. That's the only real difference here. So, something not quite related to that. Let's imagine we've got a relatively simple circuit here. And I've got whatever's going on with this thing right now, and then I close the switch. What happens to the current going through the battery? I'm looking for guesses very, very quick here. I don't want to turn off the microphone. I want to just keep going through this thing. Think about it real quick. Come up with an answer. In 5, 4, I know you can't see all my fingers. 3, 2, 1. All right, the current is going to increase, but let's talk about why. What we see right here, when we start, is a single battery, a single resistor. This openness to this end of the circuit means that no current can travel through that side. It's only going through R1. We close that switch. Now we have two resistors in parallel. Two resistors in parallel means that the resistance will go down. Delta V is equal to IR. The battery has not changed. The battery is still providing delta V the entire time. But if the resistance goes down, the current has to go up to compensate. Right, there's more than one way to actually draw these things in series or in parallel. In series, there's really one way. In parallel, there's more than one way to draw these things, right? For example, I can draw these things out. Let's imagine something real quick. So let me draw this thing out real quick. Oh, I wanted that in black. So let's imagine this is kind of like what we have been seeing so far. Something like this. Let me erase a tiny spot right here. A little bit more, a little bit more. Battery. 1 resistor, 2 resistor, 3 resistor, right? This is how we've been visualizing parallel resistors so far. And if we had one current come in, one current comes in, splits off into I1, I2, and I3. Okay, let me draw something else. I don't know why I didn't, I thought I had drawn the box, but I guess not. This right, let me space that just a little bit nicer. That's a little bit more even, except for the bottom line. Get rid of that real quick. Beautiful. Got that precision control over my hand, right? No mistakes whatsoever. So let's put our battery right here now. 1 resistor, 2 resistor, 3 resistor. These are equal pictures. They're saying the exact same thing. Current comes in, splits off, I1, and then I'm going to call this IA for now. I come up to another junction. IA splits into I2 and I3. Can we all agree that IA is equal to I2 plus I3? Then I splits into 1, 2, and 3, just like it did before. These pictures are exactly the same. There's no difference between these two. So keep that in mind, right? There are different ways to write some of these things, so don't be spooked if you see these drawn in a weird way or something else like that. That'll happen sometimes, and it's not a big deal. Just reason yourself through it. If you have to, draw out pictures like this. Label all of these currents. Keep track of these things. It helps, I promise. Been doing this long enough. I kind of know. So, one more problem for the day, and this one's maybe a little bit more practical. Let's talk about what happens when you have a car battery that's gone dead and you're trying to start it again, right? You're trying to get a jump. So, car batteries are kind of unique devices. You can touch both ends, both terminals, and you're totally fine. It's 12 volts. It's really not that much. It's not a dangerous amount or anything else. I can reasonably touch 15 volts up to 20. I don't know if I'd want to touch 30, but anywhere around in there, I think I would feel comfortable touching both ends of that thing, and I wouldn't feel a shock because the human body is a conductor, but it's really not a good one. It takes a little bit of a push to get some current moving through the human body. So anything like that, I'm really not worried about it. However, where these things excel and why they're so large is because they have to provide a ton of current. That's why they're so large in the first place, right? The idea here is that they have to store all of this energy to actually get the car started, to push out all of this current, because real batteries that we would normally see, AA batteries, I've been kind of lying to you here. Batteries have what's called an internal resistance. And it means that there's essentially a cap on how much current can actually be coming out of a real battery. Right? If you have done the lab, then you would see some of these batteries are providing pretty insane currents. And that's not quite what happens, right? They're not realistic batteries in that sense. Because realistic batteries will cap out at a certain current. They're just not able to provide anymore. And it depends on the structure, the internal resistance, a bunch of other details. Car batteries are set up in such a way to provide a lot of current before they start to cap out. And we'll see exactly how much by the time we end this. But when they start to go bad, what happens is that the oxides start to crystallize and they're no longer passing back and forth between the internal plates. So there's less conductors moving back and forth between them. The potential is starting to die. It's like any of your old Game Boys or anything else when you see that light start to get a little bit more faint, right? The voltage is starting to die. But most importantly, the internal resistance skyrockets. And 0.5 ohms is not a lot of internal resistance, but it is more than enough to stop this thing from starting properly. Anybody that has had a car that is not quite dead battery, but almost there, it kind of sputters, right? Like the lights are really faint. It almost starts, but not quite. So when you get a jump, assuming it's a good battery, it's going to have all of those ideal characteristics, very, very low internal resistance and a nice steady 12 volts. What I want to find here is how much current goes through each component. The good battery, the dead battery, the motor. Very similar to what we've just been working on, but some more realistic numbers this time around. All right, you want to start taking a look? Let's go ahead. So, it's not going to be anything much crazier than what we have been seeing so far. Right, and again, setting up the loops is the most important thing here because, like, once you get to the system of equations, you can plug this into a matrix solver for you, and I'm not concerned about that step. If you don't know how to use a matrix solver already, please do look into that one. It just speeds up this entire process. All of this solving stuff, you just need to worry about the physics, setting up the loop rules, and all of that stuff, and then once you've got that plugged into a matrix, it's solved out for you. So I do highly recommend looking into that. So, I need to make some guesses. So let's do this. Let me go with the same idea from last time, right? It comes from the positive end of the battery and goes into the negative end. So that would mean that this quantity right here, call this I of G, I of the good battery. Then we would also have I of D, current from the dead battery. And then finally we would have, let's assume I of G and ID come in. So it goes like this through the motor. That seems reasonable. Okay, then my equation right here would tell me I of G plus I of D is equal to I of M. Both batteries work together to get the motor started. That makes sense. So, now let's do some loops. And I'm going to change this one up just a little bit. I want to try and make some loops with the fewest number of components in them each. So what I'm going to do is I'm actually going to take an outside loop. Like this. And I'll start right here. So that means the first thing that I see is my 12-volt battery, and then I go with the current through my 0.01 ohm resistor. So this is 0.01 times I of G. Then I keep going, keep going, keep going. I go with the current through the motor, so that is 0.05 minus 0.05 times IM. Then back to my starting point. Blue loop. Gonna go right through here. Start at this point. 8 minus 0.5, that's super high internal resistance, minus 0.05 I of M. Okay. Now that I've got these, same process, right? That's what we're gonna get into with this. I of D and I of M, there's some things that I just don't know in these pieces. So what I'm going to do is I'm going to go ahead and plug in what I've got here. I want to put these things in terms of D and M, so I'm going to replace I of G. I'm going to say this becomes I of M minus I of D. Plug it into the red equation. Ugh. In red, please. Thank you. 12 minus 0.01 times IM minus ID minus 0.05 I of M. Okay, go through the same steps. I mean, it comes out to be a lot of similar things here, right? I think a lot of this is not super crazy at this point. It's like the same process each time for these solvings. It's not always going to be the same. This is just kind of circumstantially when we're dealing with circuits like this that just have like 3 individual lines, we see a lot of the same thing. So we've got all these, and then I look at this and I say, is there anything that I could reasonably just get rid of and destroy all at once? And no, there is not. This is the one exception on that one. I can't just subtract one of the equations away, so I'm going to have to work at this a little bit more. Let's go ahead and solve out for one of these real quick. Let me say, for example, I could say that I of D is equal to 8 minus 0.05 I of M. See, this is my sales pitch for the matricing method, because this is a whole bunch of nonsense. Like, it is a whole bunch of nonsense. I'm not going to pretend it's not a whole bunch of nonsense altogether at once here. This would be significantly easier if you just went the matricing method. But I'm committed to this thing, so this is 16 minus 0.5 of that is going to get rid of, this is going to turn into 0.1. Go ahead and plug it in. Put a little tail on that, make it look like an actual 1. Plug it into our red equation. All this stuff. Keep going with it. So this is 12 minus 0.01 times 16. That becomes 0.16. So this is 12 minus 0.16. Before I get that, I know what that number is. Minus, now this is 0.01 times 0.1, so 0.001. Oh, but it's a plus. So that's nasty. Something like that. Solved out when we plug in all of these numbers together. I'll go ahead and actually just plug this in just to make sure that all of the math so far has been all right. A little bit off from what I'm expecting to see here. Yeah, I'm a little bit off. Okay. Something is a slight goof. When you plug in this number, you should be finding that I of m is equal to 199.57. That's what we should be getting. I am off by 0.9 for some reason. I don't know if I have put something in somewhere slightly wrong or what I might have done. But something somewhere has gone slightly wrong. So, I think what it is that this method would have been fine, but I think there's a slight difference in the rounding between what I had done and what's on the solution here, and I think I scrunched up the Canvas solution a little bit too closely. So if anybody watching this sometime later found that you got question 3 wrong, but you're pretty positive you had it, or you had something very close and it should have been taken, I should have expanded that out just a little bit. But I don't want to undo the answers that people have put in so far. So please let me know if you're coming back to this sometime later and found that you were one of those people. Let me know what was up and I will get that fixed up for you. With that answer, though, we would end up finding that the I from the dead battery, if we plug that back in, is actually going to be negative 3.934. And this is why I'm kind of, I could spend the last 5 minutes trying to solve this thing out and figure out where the mistake is, but I want to talk about this result just a little bit more here. And then I of G, going back up to that initial equation at the very beginning, should be 203.5 amps. And this is a really, really, really cool result. But we guessed wrong with the dead battery. The dead battery doesn't help, it actually takes away. And this is actually why, when you're talking about getting a car jump-started, this is where we plug in everything, and this is why you have to have the second car running, right? The red jumper, the positive terminal goes to the positive terminal of the dead battery. And then you have a ground going somewhere else, generally speaking. But one of the big reasons that you want to make sure that the second car is running the entire time you do this is because it's being drained 200 amps when the car tries to start. And even if we weren't trying to start the car, a lot of this is just going into the dead battery. And if that's not enough to charge up the battery, then you're just going to end up with 2 dead batteries. So keep that in mind. That's why we actually have these things set up in such a way. When the car's running, the alternator's spinning, we're charging up the battery continuously, right? So we don't need to worry about draining the battery in that sense, though you don't want to keep it on too long. But you're not actively draining the battery anymore. There's some charge coming back into it. But it's kind of an interesting thing because it's not quite the case of what we saw last time. Because the potentials are not so different. It's really the resistances that makes the big deal. 8 volts mostly gets eaten up by my 0.5 ohms, whereas 12 volts is barely affected by 0.01. So that's going to end up pushing current through both of these other paths. And that's the kind of thing we expect to see. So somebody brought up in the last lecture, actually, he had a friend or somebody he knew working on cars and was wearing a wedding ring and accidentally touched some things that he shouldn't have and burned his hand, essentially, right? Seared a scar into his hand because of where that ring was. And the reason that might happen is because, again, we have a massive current. Remember that gold is a fantastic conductor, one of the best. And if you accidentally short something with a gold ring on your hand, there's a ton of current passing through that, on the order of 200 amps of current passing through that. It doesn't have to be a lot of voltage to get all of that power. If power is I times delta V, 12 volts times 200 amps, you're looking at 2,400 watts. A space heater is like 900. So imagine putting 2.5 space heaters around your finger all at once. Not a good idea. But touching both terminals with your fingers is totally fine. It's kind of a funny thing. All right, team. Well, if there's no questions or anything else, I think we'll call it there for the day.